due to easier of making the simulations. This shows that the tissue directly exposed to the laser. No, I'm still remaining the first slide. Thank you very much. This shows that the tissue directly exposed to the laser is more vulnerable to thermal damage than surrounding areas. The localized heating effect supports findings in laser therapy research, where targeted damage helps treat diseased tissue while protecting healthy regions. This controlled thermal response is one of the key benefits of laser-based medical treatments. In figure B, you can see the simulation that matches the first figure, figure A, at the origin, but then it's completely different, showing a rapid temperature rise at the laser site, reaching up to 90 degrees Celsius. This spike reflects the focused absorption of laser energy and highlights the importance of modeling heat propagation with spatial precisions. Figure C, as you can see, presents an increased target diameter up to 3 millimeters, which causes the thermal relaxation time to nearly double. This slows down heat propagation and lowers the peak temperature at the origin to around 41 degrees, much lower than the one in figure B. With a larger laser spot, the energy spreads over a wider area, creating a more even heating profile and reducing localized thermal buildup. Go to the next slide, please. You can go to slide 5. Thank you. Figure D offers valuable insight into how heat spreads through biological tissue when exposed to localized laser heating. The temperature distribution follows a clear spatial gradient, which is important for treatment. The thermal fields show minimal variation, meaning temperature peaks stay highly localized. This confirms that heat is effectively confined to the target area, making the simulation ideal for selectively destroying diseased tissue while protecting nearby healthy regions. The smooth gradient along both the X and Y axis suggests that the heat dissipates gradually, helping to avoid excessive thermal stress in surrounding tissue. Figure E shows a simulation using a short thermal relaxation time of 0.01 seconds, much shorter than all the thermal relaxation times used in all the other simulations. Due to the fact that heat doesn't spread far, this setup is especially useful for laser-assisted skin cancer treatments. The short relaxation times allows for fast and efficient energy absorption, producing immediate therapeutic effects without overheating deeper layers. This localized heating helps prevent unwanted tissue damage and supports faster healing and treatment. The last figures present the thermal field in a full 3D format. It uses the same thermal parameters as in figure B, but now includes the Z direction, allowing for a more complete view of heat propagation throughout the tissue volume. The highest temperature remains at the laser interaction site, and as heat spreads outward, a smooth gradient forms, decreasing along both the Z and AI axis. This behavior is especially important when dealing with non-uniform tissue structures, where differences in thermal conductivity, density, and blood flow can affect how heat moves. The simulation helps capture those effects, offering a more realistic model of laser tissue interactions. You can go to the next slide, please. In this case, we try to make mathematical validations and of all the simulation presented above. When we compared both the Mathematica, and console simulations. The figures show the thermal field distribution obtained from both numerical simulation using console and analytical calculation using Mathematica for thermal exposure times of 60 and 120 degrees. A strong agreement is observed between the two approaches. In all cases, the highest temperature approaches at the point where the laser hits and the tissue surface. From there, the temperature drops sharply in the surrounding areas, with most of the tissue staying below 45 degrees Celsius. It is known that coagulative necrosis usually begins around 60 degrees due to protein denaturation. However, the extent of thermal damage depends not only on how the tissue behaves, but also on how long it stays at the given temperature. So those simulations are extremely important to determine the surface which is going to be affected in this case when the laser hits the tissue. Despite differences in dimensionality in 3D and console versus 2D in Mathematica, the temperature contours follow a similar pattern. This suggests that the analytical model successfully captures the key physical behavior seen in the numerical simulation. Please go to the next slide, to the conclusions. So my study presents a three-dimensional analytical model based on an extended version of the Penne's bioheat equation using a non-Fourier framework. By incorporating Dirac delta functions and the telegraph equation, the model captures localized heating and finite speed thermal propagation, essential for accurately simulation laser tissue interactions. The Dirac delta functions represent sharply focused energy input, while the telegraph equation introduces a realistic time delay in the heat conduction. Together, those elements improve prediction of heat transfer in skin and subcutaneous tissue, especially under ultrafast laser exposures. Simulation using Mathematica and consoles were performed across exposure duration from 0.01 seconds to 120 seconds. Results showed that exposure time strongly influenced both the depth of the lateral spread of heat as well as the risk of thermal damage. Short pulses under 1 second keep heat localized, minimizing harm to surrounding tissue. Longer exposure, 60 to 120 seconds, allow heat to diffuse more broadly, with peak temperature reaching 70 to 100 degrees and thermal spread extending to several millimeters. Precise control of laser parameters, such as intensity, duration, and spot size, is critical. Inadequate control can lead to undertreatment or overheating, causing blistering, scarring, or delay healing. Real-time temperature monitoring and validated models like this one are essential for safe and effective laser therapy. The model also shows the longer exposure can result in lateral heat spread up to 4 to 6 millimeters, with tissue volumes reaching critical threshold for protein denaturation and coagulative necrosis. Those findings highlight the importance of careful treatment planning, including cooling strategies and accurate targeting to avoid unintended injury. Thank you very much. Can you go to the next slide, please? Here, this study is based on an article we just published this year. And the acknowledgement was funded by the Nucleo project and a series of ELI and PED projects. Thank you very much for your attentions. Do you have any questions?
Thank you very much for the presentation. Very interesting work. If there are questions from the audience or from the online, please. If no, please, Mr. Kihaya, continue.
Okay, thank you. The next presentation will be multi-scale modeling of a non-enzymatic glucose detector done by Dr. Adrian Moraru.
Okay.
Hello, my name is Adrian Moravu, and today I'm going to talk about my work called multi-scale modeling of a non-enzymatic glucose detector. On this slide, we have the contents of the presentation. First of all, why I chose to study this type of detectors, because usually we have enzymatic-based detectors, which are very expensive. Some types of structures use thicker enzyme layer, which hinders electron transport. And also, we have higher chance for interactions with different interference. Because of that, the attentions have been diverted to non-enzymatic detectors, which uses precious metals such as platinum or gold. Also, there are some glassy carbon functionalized electrodes and oxidic electrodes. In my study, I chose a nickel oxide electrode, and I also added a hybrid layer of titanite and zinc oxide, which will give us some interesting properties later. In this table are the dimensional parameters of the detector used in the calculations later. First of all, I simulated the density of states for the nickel oxide electrode. By using tighter model Slater-Costed tight binding Slater-Costed model, and by integrating all over the energy spectrum and reporting to the area, I determined the density of sites on the surface of the electrode on which glucose and other interference would attach themselves. Also, I simulated the blank CV loop, from which I determined the baseline current that will be used later in electrochemical calculations. For the absorption constants, I tried the Langmuir-Isotherm model, which is the basic model for absorption. However, as you can see, the data did not give us anything good. So I tried an alternative model, Langmuir-Isotherm model, which gave us very good results. This does not change the absorption model per se, but gives us an insight on how the interaction might work. So for the calculations of surface coverage, I used Langmuir-Isotherm absorption constants. For microkinetics, first of all, I want to talk about the detection steps, which are electrode reactivation, glucose absorption, catalytic oxidation, and Faraday current generation. From all of this, the determining step is the catalytic oxidation, because it uses the glucose and oxidizes it, compared to the electrode reactivation step, which just generates nickel trivalent nickel species on which the glucose will attach themselves. And I determined the Faraday current being 0.01 amperes, which is very low. This gives us an insight on the mechanism. It's not the Faraday current the mechanism, it's a capacitive one. And for the Faraday current, I simulated the nickel bivalent and trivalent non-incident behavior, obtained the service coverage curve, which was used for the current calculation. Next, I simulated the Butler-Volmer equation to determine the constant of the constant alpha, which gives us the symmetry of the process, and the J0, which is the basically is the speed of the electrons during the detection process. By plotting them on in a very high energy level, we over potential interval from 50 to 100 millivolts. I plotted the table plot and it obtained the value for alpha of 0.1, which means that the process is either highly redox on one side of the reaction, which is not in according to the Faraday model presented earlier. So from this we can clearly say that the absorption, that the kinetics is not absorption controlled, but diffusion controlled, and that we have capacitive model, which is more present in non-enzymatic systems. Then I tried to simulate the functional parameters of the detector to see its performance. First of all, I simulated the CV loops for different glucose concentrations. The oxidation window was from 0 to 0.75, which based on the literature, it is feasible. I obtained the calibration curve, and the limit of detection was 0.736 micrometers for glucose. Then I simulated the selectivity of the detector compared to the most common interference: ascorbic acid, uric acid, dopamine, acetaminophen, acetylsalicylic acid, lactate, and glutathione. For selectivity, I chose two approaches, one from the laboratory site, in which all interference had the same concentrations, being 5 millimoles, and another one from the working part of the detector, in which each interference had the physiological concentration present in blood. As you can see, most of the interference have clear selectivity compared to glucose. The most important one is dopamine, which has a very low value for selectivity, which means that is the main interferent that will give us problem in the future. This problem can be easily countered by using special functionalization of the surface. So by altering the surface chemistry of the electrode, we can change the selectivity of dopamine. Compared to classical enzymatic detectors, this type of system, as you can see, has a very, I'd like to say, constant variation of selectivity, which allows us to change things easier and make it so that the glucose can be easily detected. Next, I simulated the response time for the detector. First of all, I used the classical Cottrell model from chronoamperometry data. As you can see, the response time went straight to 0 because in this model, the current decreases in time, which may be true for absorption models, but because as I demonstrated earlier, we have a diffusion control mechanism. The currents should increase in time as glucose approaches the surface of the electrode, which was true in an exponential kinetics model, which gave us a response time of 3.5 seconds, which compared to literature data for various nickel oxide-based electrodes is very good value, as most of them have around 2 to 5 seconds response time. In the end, I tried to look at the retention and fatigue of the detector because the commercial one would be used constantly. For the evolution of sensor sensitivity in time, we can see that it decreases in time. After around 20 days, we have a decrease of half in the sensitivity. For the predicted peak response versus repeated uses, again, after of 175 to 100 uses, the peak response reaches around half of the initial value. And after 7 days, the sensor output has a very low variation, which allows us to use it on multiple periods of time. In the end, because I talked about the hybrid layer, it may introduce the self-powering feature. First of all, I calculated the stiffness matrix for the whole detector, which can be later used, if needed, to determine Young modulus and bulk mechanical resistance. By computing the ferroelectric and piezoelectric currents from the barium titanate and zinc oxide materials used earlier, we can see that just by pressing on the surface of the detector, because I chose a value of just putting your finger on the detector, because that's how we would use it. We have a 10.3 microampere current. That means that we need less current to operate the electrical parts of the detector. In conclusion, during this study, I was able to gain some knowledge about the mathematical background of chemical glucose detectors, and that this type of modeling may help us predict and understand the applications and abilities of this type of detectors for manufacturing them and optimizing them. For the future, I would like to try the capacitive and diffusion models that are highly likely to match the obtained data, and to produce this type of detector and compare the experimental side with the calculations made, so that I can confidently say if this type of approach is helpful or not. Thank you for your attention.
If there are questions, everyone. No. Thank you again. Next. Next presentation will be given by Ciprian Agoye from National Institute for Non-Ferrous and Rare Metals, with a presentation exploring the potential of prompt engineering in atomic scale model calculations.
Mr. Ciprian, we can see you, but we cannot hear you. Your mic is not working. It seems like it's opened, but we cannot hear you.
Something.
No, it's not from us. No, we cannot hear you. No.
Okay, maybe there is some problem, and I propose to go now to the next presentation, which will be done by Professor Viorel Chihaya. It's DFT calculations on energetic and electronic properties of interfaces in magnesium-based systems for hydrogen storage.
But Mr. Ciprian, can you stop sharing? Because I need to share. Okay, thank you.
Okay. I will present some results about interfaces which appear in magnesium-based materials for hydrogen storage. So outline will be the discussion about hydrogen storage, why we need it. Then about the computer simulation methods in general, and then how we model the interfaces and grain boundaries, and then some results about these systems. So hydrogen storage is a very important problem, technological problem, because this is a solution for green energy. There are many ways to store the hydrogen, but the most important one for mobile solution is metal-based hydrates, and especially the magnesium-based hydrates. Now, why we need simulation? By experiment, we can measure different parameters. We can use the theory to make connection between these parameters, but to go deeper in atomistic level, we need simulation methods. Here are some examples of different systems, chemical systems, and different methods which are scaling from atomistic to macro scale. So there are different kinds of methods which can be used, which are specific and can be used for a different scale of space and time. If we take such kind of method, quantum chemical method, and we take two atoms of hydrogen and we calculate the energy of these systems for different distances, we can draw such a curve which can be eventually interpolated by some analytical formula, and from this one we can discuss after that the interaction between different atoms based on empirical forces. If we come to our problem, we may know that there are at least five experimental structures of magnesium hydride. Here I use a theoretical one, so it is a virtual structure. And based on ab initio methods and thermodynamic calculations, we can calculate the energy of such systems, function of the volume. And we can draw such curves for each of these polymorphs. And from these curves, we can use a fitting formula like Monkham equation of state, which connects the energy of the minimum of these curves, the bulk modulus, the volume of the system, the equilibrium volume, which corresponds to this minimum, and the derivative of bulk modulus. So we can characterize mechanically the system. And from the derivative of energy function of the volume, we can calculate the ratio which corresponds to each point along these curves. To have an idea about the accuracy of total energy calculation with such methods, we have here the relative residual errors for cohesive energy. You can see that they are almost along this line. There are some very important errors, but are also very nice precise values. These are compared with experimental values. We can go, for example, to see the equilibrium volume for each element. We see again very nice arrangement, but also some large deviations. For the bulk modulus values, we can see that also they are very well reproduced by calculation that the experimental value. Coming back to these polymorphs of magnesium hydride, we can calculate the vibration of these systems And from the vibration of these systems, we can calculate the Gibbs energy of each system for different pressure and temperature. And by crossing this surface Gibbs energy function of temperature and pressure, we can draw the separation lines between the different polymorphs, the stability of the different polymorphs. And we can see here that at low pressure and room temperatures, alpha is the most stable one. And at higher pressures, the gamma is the stable one. And these materials are decomposing in magnesium and hydrogen gas, starting from 500 Kelvin. So we would like to change the conditions such that this release of the hydrogen to happen at lower temperature. And why is this important is that in this area, even we say that gamma is the most stable. Here, the energy Gibbs energy differences between the different polymers are very small, and actually they are coexisting. And this is also what the experiment is saying. So from X-ray, you can see that there are different structures coexisting in the same thermodynamic conditions, which can be seen in high resolution term that we have different areas which are specific to different materials. And these are identified by the distance between the different rows. So this is corresponding to the distance between different parallel surfaces. So in reality, we have pieces, so some domains which are characterized by different polymorphs structures. So this is, as we can see in 3D, there are pieces with different polymorph structures or different orientations of these grains. Here we have the same structure, and we can see here the different interfaces. For example, magnesium, alpha magnesium with magnesium, hexagonal magnesium. Gamma, magnesium hydride with alpha magnesium hydride. Or the same material, alpha, but with different orientations. And we can see that we may have such kind of interfaces, which can be done by slipping of the material. So it's the same phase, only that due to some mechanical action, they are shifted, they are slid along one direction, or they are rotated along one axis, which is in the plane, in their common plane, or it is twisted around the axis which is perpendicular on the common plane. So in practice, what we do, based on the atomistic models, so these small pieces are atoms, magnesium atoms, green, and white, they are hydrogen atoms. So we can use a periodic model, so they are reproduced in all the three directions, X, Y, Z. Or we can just have a slab with only one interface here. And we may have the same system, but fixing the top and bottom faces to the bulk of that materials. And we can characterize also, because we can determine the energy, total energy of each component, we can calculate the grain boundary energy. So there's a difference between the energy of the two interfaces model and the separated energies of the volume of that two slabs. So we can talk about homogeneous grains. So the same material, just that they are oriented in different way, or they are slided. Like here, so if we start with this is the unit cell of alpha magnesium hydride, we can build a column, let's say 10 such unit cell along C direction. Then we can determine a plane of cutting, and we do the cleavage. So we separate the two materials, and then we shift one and put it back. So this is the way how we can prepare such a slipping grain boundary. So here we did the separation, and here we just move laterally the one slab, and then we put them together. So here is the initial structure. I multiplied it twice in order to see the models. This is after a full optimization. So you can see that the atoms are rearranging, and the magnesium atoms are reforming the structure in this interface. Here it's I performed 50 picoseconds of molecular dynamics, so very short moving of the atoms. And then I increased the temperature, and here is the final after optimization, again after optimization. And we could, in this way, we could see that in the interface. So this is just the interface. This is the regular structure. And here we identified in the interface that there are some models, and these models actually correspond to some magnesium or magnesium hydride structures. Here I just took such a system and I twisted. And here I represented the band structure. These are the electronic levels, function of the K numbers. And here are the density of states. These are for the ideal magnesium hydride. So these are the conduction band, and this is the valence band. And this is the Fermi level. And just by this defect creating, we see that the band structure is quite different. And also the density of states are similar but not identical. So we have to make the remark that here the scale are different. So after creating of this grain boundary, we have enlargement of the bands, but also the band gap disappear here. So the system become metallic one. And this is just because in this area, where is the interface, if you see, these are the electronic density on hydrogen atoms. Here in a normal structure, but here at the interface, we can see that we have a continuous connection between these lobes, which means that the electrons are delocalized in the interface area. And that is the reason why we have here the Fermi level, it is in the conduction band. So we can create different other structures just by inversion. So by symmetry in this plane. And we can combine to put these unit cells together and to create such a tilted grain boundary. You see here, this is the structure before the optimization, and this is after optimization. So actually, the magnesium atoms are changing the frame in this area. So you see these are in different inclinations. So there are different orientation of the faces. But in this area, it appears a reconstruction of the system. And as consequences, we can see here the charge of each atom. So we can see that in this interface, the charges are different on different types of atoms than in the bulk area. And we can see this also on this. Here is much clearer the structure. You see here after optimization, we have a reconstruction here. And this is again twisted. So this is a much larger system. And we can see that for all these systems, they in the interface area appear a different distribution of electronic density. So here down are the charges on each hydrogen atom. So if you see here, the charges are much, actually not much, but higher than in the bulk area. And this is isosurface of electronic density. Here you see there are some localized structures. These were homogeneous grain boundaries, which means the same material, but just because the different orientation of the grains. Here we have two different interface of two different structures, which we saw that they appear in the experiment. So we can take this gamma unit cell, and I transform a bit the unit cell in order to have a magnesium on the edges of the unit cell to be compatible with alpha, the magnesium hydride. And here I created such interfaces. So you see here, this is alpha, and this is gamma. So we have in this case two interfaces, and we can perform the calculations in the same way. And we can see that here again, we have a different distribution of electronic density. Here are atomic charges. You can see the values are different than in bulk. We can create also interfaces. And here I create the interface between alpha, magnesium hydride, and hexagonal magnesium. You see, in this case, we have here the electronic density is concentrated on the hydrogen atoms. And here, if we change, because these are ISO values, we take larger values of electronic density, we'll see that here in the magnesium area, they are almost continuous. These electrons are spread everywhere. So they are here have metallic character, and here they have covalent character. You see also here the charges. Here the charges are 0 in the bulk of magnesium. The interface is, they start to be negative, 0.08. And the contact with the hydride is 0.9. Actually, if we calculate, we can calculate also the diffusion to characterize the diffusion of the magnesium and the hydrogen atoms at the interface or in the bulk. And we'll see that here it's much easier to break the bonds formed by magnesium and the hydrogen. So that means that at the grain boundary, the diffusion of the hydrogen is much higher than in the bulk. So actually, when we have such polymorphs, the diffusion of the hydrogen will be along the grain boundaries. Okay, so I can say more, but I'll stop here my presentation. And I want to thank to financial support made by UFCDI, and they paid us, supported our studies in this project, combined experimental and computational framework for hydrogen storage on magnesium-based nanoparticles. Thank you very much.
Thank you very much, Professor Vioriki Chaya. Very interesting presentation. One question from audience, if you have, please, or from the online. Okay, well, I have just one small question. Such kind of approach can be used also for the magnesium with metals alloys, or it's different?
So in the case of alloys, in principle, the answer is yes. But the problem with alloys is the large number of atoms what you have to consider in order to have a real alloy. I mean, to have a random arrangement of, or pseudo-random arrangement of the atoms in the alloy. But in principle, yes, we can do such kind of calculations. And here is the nice part of the simulation work, that all the time you can reduce the accuracy of the calculations and you can increase the number of atoms. So you have this freedom, but you have to be careful not to decrease too much the quality of the especially of the Hamiltonian of the method, because then you put under question the quality of your results. But in principle, the answer is yes. It is depending on the computational power what you have available.
I see, yes, I understand. Okay. Okay, thank you very much. And let's see if Ciprian Nagoe can now enter in contact with us.
Okay, so can you hear me, please?
Yes. Now
Can you hear me? Yes?
Yes.
Okay, thank you. So sorry for the previous problem. I will share my screen. So what I wanted to show you today is an insight from a perspective from a software developer. I'm also a researcher, but right now I'm doing software development, and you heard a lot about vibe coding and how AI takes over on software development. So how this works? I mean, we are feeding large language models with all kind of suppositions that we make and publish in our papers. So Those large language models on which those chats like Copilot are based, they are learning from us and they are able to somehow mimic the way we are thinking about problems. And this is not only about the software, it's also about how to resolve problems in science, like material science. So those models, they cost enormous amount of money, so we are not able to even think about developing of our own, but we can use the ones that are already developed, and we know, or everybody knows about ChatGPT, but yeah, Copilot is something affordable from Microsoft. So then I was thinking how to put this to work. So what I am showing you is not a real simulation of model, but just how to put to work a simple chat like Copilot. And yeah, I will show you how it looks like. So this is how it looks. You can write here, ask who I am or whatever you want to ask in the chat, and it will answer. Let's say, give me periodic table, and it will think about and provide some answer. So you can see this is very simple, and typically it works. There are cases where it's not able to perform the task, but it works. And now let's think about high entropy alloys model, how this might work with Copilot. So it can do, as you saw, I just did some query about periodic tables, so it can extract from literature, it can extract tables, and it can also format them to the way we need them. It can put together columns from different tables, and all of them, they are in the literature, and the Copilot or other large language models, they learn them. So they are in the model from our papers. So then we can use that thing. Like, yeah, I showed you here a table with all kind of columns that are relevant for our model. This is also the Copilot indicated the paper from which he extracted those parameters. So it can also look for parameters, but also format them to the way we need them to feed our models. Then this is not recommended, but I just showed you because it can perform calculations. So I asked Copilot to calculate something, and yeah, about the Maya-Dema model, and it did some calculations, provided some relevant parameters, also provided some references, literature references, and explained me what to do with those parameters. So it's able to do this. Then I asked Copilot to perform some, to do some visualizations of the data. And well, after some thinking, it could plot some graphs in a relevant manner. So you can do this also. You have data and you want to visualize them, and you probably, well, if you really know what to do with them and have enough time, you can plot them yourself with Excel or other performant graphic applications. But you can also get some pre-visualizations, let's say it like this, from Copilot. Then one thing that is widely used in the software industry is a coding assistant from Copilot. Well, we use some specialized, not this Copilot, but a specialized trained Copilot, GitHub Copilot. But I ask this normal Copilot that we have here, I ask this guy to perform some programming for me. So I asked him to create a script that will show an HTML page with a button. So it did. It provided the code, explained me how to start the application, and yeah, I could see that on Chrome. So it can do this, and yes, it's very potent. I can tell you, in software industry is widely used to refactor code, but it has some flaws. You know, as a joke, there is this job as a cleanup software developer. It means after Copilot did the job, you need a very experienced software developer to clean what Copilot did wrong. But essentially, it can create applications if you correctly guide it. So why I'm saying this? Because we have applications that they are custom, and we can upgrade them, and we can put them to our work without very much effort or knowledge about coding. By using Copilot, and it can do it especially for small scripts that we typically use to format data or do all kind of small tasks around our main job. But how do we know the calculations that Copilot provided are correct, or any other prompt engineering output is correct? We don't. We need a validation, like we need for our models in this branch. Validation can be obtained, of course, by experiments. This is the gold standard. We do experiments with real materials and we validate, but it's limited. We cannot have very fine details about all kind of parameters that we use in modeling. We are very much limited, but we have our software, our existing models, and we can put them to work in a way that it can work with those prompt engineering techniques and applications. They can provide the feedback those applications, those large language models based applications need to go on. Those Copilot or other GPT based applications, they are able to work as agents, which means not only answer the questions but go forward using strategies that they learned from us, from our papers, from our work, and proposed some things, some strategies to mix atoms, metals, in a way that we thought about in papers, but we are not always focused on that. And they can propose those things and say, what if you can do this, and go to some output. And what we need is to restrict the amount of, let's say, hallucinations sometimes, the amount of data that those prompt engineering techniques produce by doing some validation in front and provide it as output to those agents. So this is what we learned from software development. We have there the compiler. The compiler is especially for those very strict languages, is the truth for what you wrote as a code. If the compiler says is not okay, you have some mistakes, then it will immediately, Copilot or other agent will immediately correct. But to correct, it needs to refer to something that it knows as terms, as coins from the literature. So if you provide an application as the output of an application, a normal calculation model, as feedback for the agent, you need to log those validity rules, in a way they are implemented in literature. And for that, you can also ask Copilot. So it's a closed circle. You ask Copilot about validation rule, and then in the software that you did to do the model calculations, you provide logs that are understandable for it. And it will then go to the next strategy. And this way you can speed up the process of creating models based on the help of an automated system that will get the feedback and provide something better and better, improve itself. Well, this is a theory, but we don't know how it works. So it's just a proposal. And yeah, don't give up on model calculations that you have to go to the AI, because AI needs those calculations that are the truth in our theories. Thank you.
Thank you. If there are questions, please, from the audience or from the online. Okay, if not, Professor Viorel Quijaya, please take the floor.
Thank you. Thank you. We have an additional one, aluminothermic fuels by Sabina Fironda from Institute of Non-Ferrous Materials and Rare Metals. Is it online?
Sabina? We see the presentation, but we don't hear you.
Să fac prezentarea în limba română. Ați aici. Combustibil aluminaterici, găsiți.
Faceți dumneavoastră?
Da.
Ok, Sabina, să
Păi văd că
prezinte,
n-a venit acum.
să prezinte domnul Adrian Coman.
Da.
Can you stop sharing?
Combustibil? E. Deci dacă nu găsiți, încercați-l pe ăsta. Combustibil aluminaterici, PowerPoint. Nu, trebuie să fie mai puțin, pe că l-am venit că să des.
Asta.
Asta e.
Sabina, stop share, please.
Dacă apar întrebări, dumneavoastră o să știe în limba engleză și eu o să traduc. Dați numai așa.
Gata.
Adică...
Pe ce ai dat?
Săgețele.
Ăsta?
Stai un pic, că vine imediat să mă uit.
Microphones, please, Ana.
Deci, noțiunea de combustibil aluminaterici este de fapt o metaforă și a pornit de la definiția combustibililor și de la definiția arderii, coroborate cu existența pe teritoriul României și nu numai, a unor vaste depozite de țundere care sunt oxizi ai oțelurilor. Aici avem niște definiții a termenilor utilizați, cum ar fi amestecurile termitice, reactanții termitici, materialele termitice. Acestea sunt denumiri cumva specializate care vor fi utilizate pe cursul prezentării. Avem aici o schemă bloc, schemă logică de realizare a acestor combustibili aluminoteri. Ei pornesc de la materii prime, cum ar fi zundarele, pulberile de aluminiu și precursori moderatori de reacție. Se fac niște procesări și se obțin reactanți oxidici, reactanți reducători și moderatori de reacție. Materialele termitice, după cum v-am spus, sunt în principal oxizi. Cam 70% dintre materialele termitice sunt formate din oxizi. În România, depozitele de materiale oxidice sunt vaste și diferite. Însă, pentru a putea fi mai ușor de gestionat, se folosesc sundărele de la OL 37, S235. Materie ca reducători pot fi folosite pulberi de aluminiu atomizat sau pulberi rezultate din reciclarea deșeurilor de aluminiu. Moderatori de reacție sunt diferiți, cum ar fi așa. Reactanții oxidici, moderatorii de reacție sunt constituite din feroaliaje, precursori de feroaliaje, inhibitori de reacții, cum ar fi floarea de cuie sau șpanurile și fondanții. Ca să putem să ajungem la combustibili aluminotermici, trebuie ca țundările să fie separate pe compoziții chimice preponderente și o metodă rapidă care poate fi utilizată în flux continuu, pentru că mai sunt și alte metode, dar nu pot fi utilizate în flux continuu, este separarea magnetică a acestora. Și separarea magnetică utilizează faptul că cele trei tipuri de oxizi care formează țundărele au proprietăți magnetice cumva diferite. P3O4 magnetita este feromagnetică, PO-rustita este antiferomagnetică și P2O3 hematita poate fi diamagnetică sau paramagnetică în funcție de forma alotropică sau de starea ei morfologică. Forma obișnuită alfa a hematitei este paramagnetică, dar poate trece temporar într-o formă nemagnetică prin calcinarea ei la o temperatură de circa 1200 de grade în exces de aer. Parametrul care permite separarea magnetică pe cele trei componente, pe cele trei sortimente de oxizi, este forța magnetică, F, care apare la trecerea țundărilor pulverulente printr-un câmp magnetic de intensitate controlabilă, H, creat de un magnet permanent rotitor. Controlarea forței F, reglarea ei, să zicem așa, s-a făcut prin controlarea intensității câmpului magnetic și a constat în modificarea distanței D dintre suprafața magnetului rotitor și axa jetului de pulbere oxidică, în cazul nostru alfa pe 2O3, deversată prin separatorul magnetic. În această situație, după cum vedeți, expresia forței este cea de pe ecran, în care și s-au prezentat componentele formulei. Sunt obișnuite, nu e nimic deosebit aici. Partea deosebită este etapizarea separării magnetice. Și etapele tehnologice ar fi calcinarea în exces de aer, răcirea țundărilor calcinate, separarea pe clase granulometrice și urmată la final de separarea magnetică a claselor granulometrice identificate. Și se obțin astfel tipuri diferite de oxizi preponderenți. Pornind de la această realitate, a fost realizat un separator magnetic diferențial prezentat în figura 2. Schema lui bloc, schema logică, este în desenul de alături. Acum, odată ce avem țundărele separate pe componente preponderente, pe sortimente, ca să zic așa, se poate trece la realizarea rețetelor termitice. Dar rețetele termitice trebuie să ținem cont că se vor adresa unor reacții aluminotermice de tip continuu. Ele reprezintă sortimente alcătuite procentual din componentele respective. Numai că rețetele termitice folosite pentru materializarea reacțiilor aluminotermice de tip continuu trebuie să ținem cont că au două componente. Au o componentă exergonică, generatoare de energie, și este formată din reactanții termitici, adică oxid și reducători. Și o componentă endergonică, care este o componentă consumatoare de energie și este formată din moderatorii de reacție. Cele două componente permit proiectarea unui ansamblu de rețete termitice care, generând aceeași cantitate de energie, pot conduce cu anumite particularizări, modificări ale componentei moderatoare către o familie de aplicații particularizate. Rețetele termitice trebuie să ținem cont că fiecare lot de reactanți, de țundere, să zicem, de reactanți și de moderatori sunt diferite. Numai că la un moment dat se va pune problema ca să obținem aceeași calitate pentru oțelurile sau cantitatea de energie termică necesară, proiectată. Schema logică, potențiala unei familii de rețete termice este prezentată în tabelul de mai jos. După cum vedeți, avem componenta energetică, componenta de aliere și moderatorii, ceilalți moderatori. Proiectarea unei rețete termitice sau unei familii de rețete termitice începe după separarea pe granulație a lotului de țundere, urmată de separarea magnetică diferențială a fiecarei clase granulometrice de interes. Odată ce avem separate componentele țundărelor și odată ce avem rețetele termitice fundamentale ale aluminotermiei, vom reuși să alcătuim o familie de rețete care este doar teoretică, pentru că se referă la ecuațiile de echilibru stoichiometric ale aluminotermiei. Și această familie, această posibilitate relativ rapidă de determinarea unei familiei de rețete, trebuie să ținem cont că pentru a fi aplicată în reacția aluminotermice de tip continuu, trebuie cumva, să zic așa, adusă la realitatea tehnologică, metalurgică. Așa. Și pentru asta s-a întocmit o diagramă aluminiu termic, care, după cum vedeți, permite identificarea rapidă a unei anumite rețete. Și anume, dacă proiectarea oricărei reacții ține dacă de la aplicația vizată și calculele teoretice arată energia, să zicem, de care este nevoie pentru ca să se identifice ușor rețeta. După cum vedeți, avem pe linia verde orizontală, se duce orizontală și care întâlnește diagrama trasată cu linie roșie. În punctul O, dacă mergem pe verticală, obținem rețeta. Această rețetă are doar valoare teoretică. Acum, trecând, după ce am stabilit reacțiile, rețetele termitice, rețeta termitică sau familia de rețete termitice, trebuie să scoatem în evidență faptul că reacțiile aluminotermice de tip continuu, că astea sunt cele care ne interesează în acest moment, pot fi unisecvențiale atunci când lotul de țundere are aceeași compoziție chimică și când produsele de reacție sunt aceleași pentru întreg lotul, sau multisecvențiale, cum de fapt este realitatea, când rețetele termitice cumva sunt diferite, dar ele trebuie să conducă la aceleași produse de reacție. Iar reacția luminotermică de tip continuu se poate materializa într-un dispozitiv ca cel din figura care se vede, și anume este vorba despre un creuzet cu pereți dubli, făcut din grafit, răcit cu metale topite, care produce simultan și fără a consuma energie convențională, produce produse metalurgice, produse siderurgice și energie calorică. Energia calorică se știe că poate fi ușor transformată în energie electrică. Particularitatea și specificitatea acestui proces este că reușește să producă oțeluri fără a fi nevoie de coxerii, de furnale sau de convertizoare fontă-oțel. Și iarăși, tot ca o particularizare, este că simultan cu aceste produse, să zicem, metalurgice și siderurgice, apare cantitatea de căldură. Tot sistemul funcționează independent energetic, deci el se auto-întreține, producând energie. Simultan cu toate celelalte care vi le-am expus mai devreme. Specificitățile valorificabile ale reacțiilor fundamentale ale aluminotermiei sunt trecute aici cu verde, le-am și cam spus. Așa, după ce am făcut această prezentare, trebuie să vă spun că acești combustibili aluminotermici au aspectul care se vede în figura din dreapta. Deci amestecurile aluminotermice reprezintă amestecuri omogenizate. Combustibilii aluminotermici reprezintă amestecuri omogenizate alcătuite procentual din cele 3 sortimente compoziționale ale țundărelor și fulbe de aluminiu plus sortimente ale moderatorilor de reacții. Inițial, componentele combustibililor aluminotermici sunt dozate pentru a corespunde proporțiilor molare indicate de sistemul 1, care este sistemul de bază al reacțiilor aluminotermice. Componenta, deci bineînțeles că există o componentă energetică și o componentă moderatoare, pe care vi le-am prezentat înainte. Acum, dacă aplicația care o avem vizată se referă la energia calorică, atunci trebuie să vă spun, trebuie să scot în evidență faptul că fiecare dintre rețetele fundamentale ale aluminotermiei este generatoare a unei anumite cantități de energie. De asemenea, și este generatoare a anumite cantități de, să zicem, oțel sau de zburi, sau de zburi specifice, care sunt, dacă vreți, un amestec de Al2O3 și particule de oțel. Așa. De aici putem să mergem, să facem un pas mai departe și să ne gândim și să observăm, să scoatem în evidență că alcătuirea rețetelor termitice poate să conducă către, ca să zic, o etapă a doua, către cantități diferite sau alese prin proiectare să aibă o anumită valoare în funcție de cum se alcătuiesc rețetele, să zicem, termitice. Dacă avem, ca să putem să avem o bază a discuției, se observă că fiecare dintre ele dau cantități diferite de energie și de celelalte componente. Așa. Numai că, funcție de cum alegem rețetele termice, dintr-o singură componentă, din 2 componente sau din 3 componente, că, de fapt, se obțin și cantități diferite ale produselor de reacție. Deci, uitați, pentru oxidii singulari este prezentat în această figură și se vede că faptul că reacția de reducere a magnezitei generează cea mai mare cantitate de căldură, indiferent de variația temperaturii de reacție. Pentru compozițiile termitice binare, care conțin, de exemplu, magnezită și hematită, se asigură maximizarea efectului termic pentru proporțiile egale ale celor două tipuri de oxid. O majorare a proporției cărui component în detrimentul celuilalt component duce la o diminuare a efectului termic al reacției. Compozițiile termitice binare, care conțin hematită și fustită, conduc la creșterea efectului termic cu atât mai puternic cu cât proporția hematitei în amestec este mai ridicată. În cazul combinațiilor ternare, deci atunci când participă toți cei trei oxizi separați magnetic, cum am prezentat mai înainte, arată că efectul termic al reacțiilor de reducere aluminotermică a amestecurilor complexe de oxizi, deci ternare, care se știu care sunt, feros, feroferic și feric, evidențiază odată în plus rolul prezenței oxidului feroferic, P3O4. Și, în acesta și faptul că acest efect termic al reacțiilor este maxim în momentul în care sunt îndeplinite simultan condițiile care se văd. P3O4 mai mare decât PO, P2O3 mai mare decât PO, vorbesc de procente. Și P3O4 să fie aproximativ egal cu P2O3. Și se vede în aceste diagrame și alături ecuațiile, expresiile matematice ale combinațiilor prezentate mai înainte. Și am ținut să prezint niște concluzii integratoare. Și acestea, după cum vedeți, sunt cam 6 concluzii integratoare relevante și arată că, din punct de vedere termodinamic, toate reacțiile de reducere aluminotermică ale oxizilor fierului sunt posibile. Entalpiile libere de reacție ale acestora sunt negative pe tot domeniul temperaturilor de interes. Dar pentru reacțiile simple, concluzia este că oxidul feroferic este oxidul care asigură prin reducerea efectul termic cel mai puternic. În combinațiile binare, aici sunt 3 concluzii, care conțin oxidul feroferic și oxidul feros în proporții diferite, creșterea pondei magnetitei asigură o majorare a efectului termic. Și similare, dacă avem oxid feroferic și feric, efectul termic este cu atât mai puternic cu cât proporția oxidului feric este mai mare. În compozițiile termitice complexe ternare, efectul termic este cu atât mai mare, cum am prezentat și mai înainte, atunci când sunt îndeplinite cumulativ cele 3 condiții care sunt pe ultimul rând în dreapta. P3O4 mai mare decât, ca proporții, decât PO și așa mai departe. Reacțiile aluminotermice de tip continuu sunt reacții complexe, foarte valoroase, dar în același timp și periculoase. Adică, dacă le scăpăm din mână, ușor ajungem la explozii. Se știe că termiturile pot avea atât aplicații civile cât și militare. Eu sunt abilitat să utilizez doar componentele civile. Așa. Și pentru asta se pune problema controlării acestor reacții, astfel încât permanent ele să dea efecte utile fără ca să ne pună nouă viața în pericol, operatorilor sau clădirilor înconjurătoare. Ca să putem face ceea ce este important, este că viteza, sunt 2 parametri absolut importanți, sunt mai mulți, dar 2 parametri sunt, ca să zic așa, cruciali. Viteza de reacție și accelerația de reacție. Pentru ca ansamblul pe care vi l-am arătat mai sus, mai înainte, să poată funcționa, trebuie ca viteza cu care sunt consumați reactanții trebuie să fie egală cu viteza cu care iau naștere produsele de reacție. Viteza. Iar dacă vrem să avem un proces constant și de încredere, trebuie ca accelerația procesului să fie zero. Dacă este pozitivă, înseamnă că reacția trebuie oprită, dacă e negativă, înseamnă că trebuie adusă la acel zero. Așa. Și pentru aceasta a fost realizat un set de echipamente care este în figura din dreapta și care se vede, conține un laptop, un aparat complex pentru măsurarea vitezei și accelerației, a constantelor de reacție, a rezistenței electrice, a amestecului termitic și mai sunt și altele. Dar pentru că nu ne putem întinde vreo 2 ore, le-am pus aici o parte. Le-am lăsat așa. Și am început cu determinarea vitezei de reacție. Trebuie să vă spun că vitezele de reacție sunt specifice reacțiilor. Dacă avem reacții secvențiale, avem viteze de reacție, viteza reacției secvențiale și dacă avem dacă avem reacții de tip multisecvențial sau continuu, există o altă viteză de reacție de pe 2 și acolo de pe 1. Schema sau dispozitivul complex care le-am văzut acolo, are o schemă bloc care se vede în această figură și are niște componente care sunt, cum vedeți, sunt vreo 14. Aparatul complex pentru măsurări este în poziția A și sistemul experimental a fost prezentat în figura B. Acum, fiecare dintre funcțiile aparatului complex are o schemă logică a procedurului respectiv. În stânga este schema logică a procedurului de determinare a vitezei de reacție și în dreapta este schema logică a procedurului de determinare a energiei de activare a reacției. Se știe că o reacție aluminotermică poate să aibă loc atunci când, într-o anumită incintă, în cazul nostru, creuzetul din grafit, un creuzet oarecare din grafit, conține amestecul aluminotermic sau combustibilii aluminotermici în cazul nostru, dar la care trebuie din exterior să-i administrăm o energie care se cheamă energie de activare.
Puteți să vă...
Aparatura aceasta dă niște diagrame, cum ar fi intensitatea funcție, intensitatea, deci vorbesc acum despre intensitatea administrată procesorului pentru demararea lui. Și asta este intensitatea, să zicem, notată cu IS și tensiunea U0. Variația lor arată momentul în care începe reacția să se dezvolte și când se termină. Toate sunt în funcție de timp. Am mai prezentat aici, cu toate că sunt mai multe diagrame, dar pentru a condensa expunerea, am mai prezentat diagrama de variație a puterii electrice, care o vedeți în dreapta și care, bineînțeles, că pornește de la definiția puterii electrice.
Ne putem...
Puteți să încercați să concluzionați?
Da. Haideți să vă prezint, uitați-vă. Ca final, mai era așa, ca final vă arăt demararea cercetărilor experimentale și crearea bazei de încercări. În partea stângă sus este oțelăria aluminotermică care a fost realizată. Alături este prezentarea interiorului și a dispozitivelor care materializează reacțiile de tip continuu ale combustibililor, o detaliere și un lucru foarte important este că acest tip de reacții de combustibililor aluminotermici este capabil să schimbe paradigma care zice că producerea materialelor metalurgice și producerea de energie termoelectrică este poluantă și energofagă. Noi nu consumăm energie se auto-întreține, iar analizarea gazelor de ardere, arată că cantitatea de dioxid de carbon care o generează gazele de reacție este 0,09% din amestec, pe când și în atmosferă se știe că este 0,04%. Deci se vede că gazele poluante sunt de cel puțin 100 de ori mai reduse, de cel puțin 100 față de orice alt procedeu care conduce la realizarea de produse energetice sau produse metalice. În dreapta avem o imagine a modelului demonstrator care este cumva funcțional. Și dacă de pe acolo puteți dumneavoastră să dați în partea asta de așa. Și acum o să vedeți cum funcționează o oțelărie care nu are nevoie de copserii, nu are nevoie de furnale și care produce simultan atât energie termoelectrică cât și produse metalurgice. Se știe că orice termocentrală, atunci când produce energie termoelectrică, are niște materiale reziduale. Cenuși, prafuri, asta ca gazele de reacție care pot
Mulțumesc frumos.
Dacă sunt întrebări și în limba engleză, cred că e cine să răspundă și în limba engleză. Mulțumesc.
Mulțumesc frumos.
Okay, I also thanks to participants and thanks to Professor Viorel Chihaya for sharing. And you have a half an hour lunch break and then come back for the Young Poster Awards.
Okay, thank you, Dr. Pircescu. Before the break, I will thank again the Ministry of Education and Research, the European Technology Platform on Sustainable Mineral Resources, and Altium and Nano Team, the sponsors of our event. So enjoy your lunch and see you in half an hour. Thank you. Cum să vedem? Okay. So it seems that our event got to its end. We hope that our eighth international conference, EMERGEMAT, was an interesting one. And here we are at the moment when we start awarding diplomas and prizes for participants, sponsors, and so on. For the beginning, we will start with the sponsors. We have prepared, okay, we will send them, because right now the sponsor, they are not present, but we will send them via email or mail. For SECE Altium International SRL as a sponsor. The second diploma for the sponsor is for SECE Nanoteam SRL. For this time is not a sponsor diploma, but a co-organizer diploma for the European Technology Platform. And we mentioned here Mrs. Marina Kabidosh, who was very helpful for us with assuring the connection online, taking into account the number of online participants from Romania and also from abroad. And I mentioned again the Ministry for Education and Research, but this time the support was in the frame of a financing contract, so it is somehow a different thing, but we have to mention it. Okay. The next step is for prizing the young researchers who took part in our contest. And we start with section 1. The third place is for Miss or Mrs. Larisa Anda Stroe with the work influence of temperature on the material properties of carbon fiber composites manufactured using out of autoclave techniques. I think that she is from INCAS Bucharest. We have connections with them, so they will receive the prize. The next place, the second place in the same section is for Mr. Cristian Căsuț for electrical behavior of bismuth iron oxygen / bismuth 25 iron oxygen 40 silicon composites. If I remember well, is about portable devices who are able to fold and fold flexible mobile devices. The first prize in section 1 goes to Miss Melinda Vajda for sustainable PEDOT/GO counter electrodes for efficient indoor dye synthesized solar cells. And now we switch to section 2, critical raw materials. The third place to Miss Maria Bălan for VLS growth of nanostructures for laser particle acceleration application. Miss Ana Udrea gets the second place, scintillating nanoparticles drive X-ray photodynamic cancer therapy. And the first prize in this section goes to Mrs. Ștefania Caramarin for sol gel derived peptides. Okay, now section 3, new materials for environmental protection. The third place, Matei Mortic. If I'm not wrong, he is the youngest participant. He is still a pupil in high school the last year. Yeah, I won't on what I said, but fabrication and characterization of spiral face plates generated by 3D laser lithography. Da, am impresia că era un coleg de la dumneavoastră, categoric, da. Sorry for this moment, for the Romanian moment. But it was so tempting because of you. You are guilty, not me. Okay. The second place, Miss or Mrs. Raluca Ivan, tailoring functional nanohybrids by laser, again from you. Section 3 again, and the first place, Cristina Firincă, integrated bioremediation and monitoring of chromium contaminated soils using fungal consortium and electrochemical sensors. If I remember well, she is from ECHEC.
Thank you very much for this honor. I am online.
Okay.
Thank you very much.
Welcome. You deserved it according to our evaluation, and good luck for the future, for your career, and so on. And hope
Thank you
to
very
see
much.
you next year, maybe face to face, maybe again online. It depends. Okay, yeah, but let's invite them. Yeah. Okay. The last section of our event, materials modeling and simulation. The third place goes to Marian Nicolae Costea. Design of advanced multi-component alloys via direct energy deposition technology for high-performance industrial applications. Good luck. The second place, there is a group of young researchers this time. Paul Gabriel Stoica, Elena Sorina Dondea, Aura Cătălina Mocanu, Monte Carlo simulation of electron interaction volumes in thin film coatings. And the first prize goes to Eliza Petre, Elisea, yeah. Design and experimental validation of zinc oxide heterostructures. Thank you very much.
No,
Why not? Please.
No. Okay.
Okay.
Then she is from our institute, and she is working in a, let's say, a very modern department. CETAL is in Romania, Center for Advanced Laser Technologies. Yeah. Okay.
Good luck to you.
The last scientific secretary of our institute. Yeah.
And so on.
Congratulations.
To all the team. And we have the final award, the Excellence Award, I don't know. Mr. Bogdan Postolnoi, can you hear us? Are you here with us online?
Far away.
He is
Can you
online.
hear me? Hello?
Yes, I can hear you.
Yeah.
Can you see it?
Oh my God.
Can you
Yeah,
see
yes, I
it?
see it.
Okay, you just
Yeah.
see it, you don't get it.
I will come to
Okay.
take it then.
Congratulations.
Thank you so much. Thank you so much.
Yeah,
for that.
Professor
And-
Pogrebniak will bring it to you.
Yeah.
This is
Oh, I will take it. Yeah.
for his work on hair alloys.
It's necessary to fill it with some champagne, not.
No, he will. Congratulations, Bogdan.
Thank you. If I have opportunity just to say one word for everyone.
Yeah,
Just
please.
To say also thank you for the organizers. So I remember participating in that conference for several years. I think the first time in 2019 or something, when we were just connected from the cost action critical raw materials with Professor Radu Pitisescu and also Maria Luisa Grilli, who is the member of scientific committee of this conference. So it's a big pleasure, and I wish all the best for the conference, and I believe it has a great future and potential continue to grow. And congratulations to all young researchers who receive award this year, or even who didn't receive. I wish you have all the best for the next years and have new awards for you. Thank you so much.
Okay, thank you very much, Bogdan, for your nice thoughts and wishes. Thank you. And I will not end before giving a big thank you to the team of CTT Avanmat, who was deeply involved in the organization of this event. I mean, Mrs. Petricianu, the director of CTT Avanmat. I don't know where she is. Okay. I will also mention here another member of the team, Gabriela Ionita. I will thank to Mrs. Caramarin, who was all the time in front of the computer assuring the connection with all the participants. Dr. Tudor Albert, Dr. Drăguț Vasile, Valentin, sorry. I have to give you a line. Dr. Piticescu, who was involved in the scientific part. No, you are at the end. Not as Dr. Piticescu as the general manager who assured all
The merit
necessary things.
is yours and my colleagues, and also I have to thank you, you as scientific.
No, I was not a very good host. And sorry, I forgot to mention Dr. Mocioiu, Ana Maria Mocioiu, who was all the time near us and
our IT support.
yeah. So it seems that this is the end. We hope in next event, next autumn.
We have a lot of best wishes from online also.
Okay, thank you very much to all the online participants. And we are waiting for all of you next year in the 9th edition.
To complete the feedback, please.
Yeah, if you are so kind, scanning the code
feedback.
bar for the feedback of the event, please do it when you have time, when you have pleasure.
You can find also online on the site of the conference.
And I'll put it also on the chat.
Okay, so it seems that it is not very difficult to to find the way to send the feedback. Okay,
Thank you so much.
thank you so much to people here in the room and also to people online. Thank you. Asta